Hi everyone. So we are continuing our videos for section 6.1. So in this video, we're going to start talking about equivalent fractions. So the book starts talking about this on page 201. So we have just some definitions to start out. So we talk about two fractions being equivalent if they represent the same quantity. This can also be said the same value, the same quantity or the same value. So that's when two fractions are equivalent. And we typically denote equivalence just by the normal equal sign. So this should be something that you're pretty familiar with. One thing to notice is that 2/4 and 3/6 are equivalent fractions, but one is not a multiple of the other. It's really common for when we talk about equivalent fractions to say that it's multiples of one another, right? If you start with a third is equivalent to 2/6 and 3/9 and 4/12 and so on. So it's easy to explain equivalent fractions by talking about multiples of that fraction. But this is not the best way to explain it, because then your student may be faced with something like looking at 2/4 and 3/6, and what do they do with that, because they are equivalent and they're both equivalent to 1/2, but these two are not multiples of each other. So there's just that distinction to note, that equivalent fractions are indeed multiples of the fraction being in its simplest form, but not always. But if you have fractions that are multiples of that simplest form, those two things are still equivalent, even though they may not be multiple of each other. So kind of going off of that, a fraction is in simplest form when its numerator and denominator are relatively prime, meaning that relatively prime, recall from before, that relatively prime just means that the greatest common divisor in both of these numbers is 1. You cannot reduce it anymore. Right? They don't share any factors. So in the case of 2/4 and 3/6, neither of those are in simplest form, because 2 and 4 are not relatively prime because their GCD is 2. And likewise, 3 and 6 are not relatively prime because their GCD is 3. Okay, so another note just about how we say things is we tend to say simplify fractions and reduce fractions interchangeably. But just kind of the way we use reduce, kind of colloquially outside of math, reduce is typically associated with decreasing, right, as a reduction and making things smaller. So this may not be the best term to use, but with equivalent fractions, right, everything's equal, right? We have this equality between the values. So the size of the fraction doesn't change, and we may want to use reduce and avoid using reduce in favor of simplify. So use simplify so that it's more clear that the values here are not changing. Okay, so let's look at how to simplify fractions. So we can simplify fractions like so. So if we want to simplify the fraction 10/9, one way that we can do this is by looking at the factors of the numerator and denominator. So we can factor 10 as 2 and 5, and we can factor 9 as 3 and 3. So 10 and 9 don't have any common factors, so this is already in simplified form. So this is already in simplified form. So there's nothing we need to do here. It's already in simplified form because there's no common factors, right? So looking at the factors in this way is because we're checking if the numerator and denominator are relatively prime. That means that we're looking at the GCD, the greatest common factor or divisor of 10 and 9. So now let's look at 12 over 10. So 12 can be written as 2 times 2 times 3, and 10 can be written as 2 times 5. So these have a common factor of 2, so we can take that away from the top and the bottom, and then we're left with 2 times 3 on top and 5 on bottom, so this is equal to 6/5. So in this case, the simplified form is 6/5. Okay, so sometimes people will interpret simplifying fractions that are in improper form like these two as writing it as a mixed number. But we're not going to do that. That may be one way that you have heard of simplifying things or rewriting fractions in the past, is by making every improper fraction a mixed number. But like we've kind of touched on in other videos, improper fractions aren't bad. You just need to specify what form you want answers in. So if a problem doesn't tell you to specifically write an improper fraction as a mixed number to simplify it, then I don't think that that's something that you ever need to do. Okay, so now let's look at some tests for equivalent fractions. So if we have a over b and c over d as two fractions, we can do some different things to compare them, to compare the value that they represent. Okay, so the first thing we can do is just compare their simplified fractions. So we can look at their simplified fractions and see which one, if they represent the same value, meaning that in this process you will take the fractions, make them both in simplified form, and then see if they're equivalent. The next thing we can do is compare equivalent fractions with a common denominator. So rather than changing them to a simplified form, change them to a form where they both have the same denominator, and then compare them. And the last thing is to compare using cross products, which is called cross multiplication. Some people have called this the butterfly method, but this is the most common thing that people do to compare fractions to see if they are equivalent or not. Okay, so this example says determine whether 3/8 and 6/16 are equivalent. I know it says by comparing cross products, but I kind of want to go through these three different methods to see how they all work. So for part A, we want to just compare the simplified fractions. So 3/8, well, 3 is prime, so 3 just has a factor of itself, and 8 can be represented as 2 times 2 times 2. So there are no common factors here. So this is already in simplified form. So this is already in simplified form. And now let's do 6 over 16. And 6 can be written as 2 times 3. 16 is 2 times 2 times 2 times 2. So these have a common factor of 2. So we can take a factor of 2 away from the top and the bottom. And we're left with 3 over 2 times 2 times 2, which is 3 over 8. So when we reduce 6/16 to its simplified form, and we reduce both of these fractions to the simplified form, these are equivalent. By doing that, let me write that a little better. So these are equivalent. Okay, now let's do it using comparing equivalent fractions with a common denominator. So in this case, you can just pick a common denominator. So with this one, it's pretty much the exact same process, actually. If you're trying to find a common denominator between 8 and 16, you can either increase the denominator of 8 to 16 or decrease the denominator of 16 to 8. So in this case, let's go ahead and increase it to 16 just so it's a little bit easier. So if we want to have 3 over 8, have a denominator of 16, we multiply it by 2 over 2. And one thing to note here, whenever we're changing denominators, we multiply by fractions of the form of this form where we have one number over the same number. And so just something to keep in mind is that this process works because 2 over 2 is equivalent to 1. And we have this, and 1 is the multiplicative identity. So that's one thing to note, that this process, all of it, everything we kind of do here boils down to what we've talked about previously with those properties of addition, subtraction, multiplication, and division all play a part in how we do math later on. So when we multiply 3 over 8 by 2 over 2, we get 6 over 16, and we're comparing that to 6 over 16. So again, whenever you change this denominator of 8 to the denominator of 16, we're comparing 6 over 16 to 6 over 16. And again, these are equivalent. So lastly, with part C, we want to use cross product. So when we use the cross product, we group them like this. So we multiply 3 times 16, we multiply 6 times 8. So 3 times 16 is 48, and 6 times 8 is also 48. So since these are equal, so since 48 equals 48, remember that is the reflexive property of equality, we have 3 over 8 equals 6 over 16. Okay, see, like I said, everything kind of comes back down, boils down to we can do all of these things because of all these properties we spent so much time on earlier. Okay. So let's think about why comparing cross products works. This is something that we use all the time. And it's something that you may not have ever given a lot of thought to about why it works. But why this works is essentially because it's a form of making a common denominator. So when we did in part B, whenever we found a common denominator, we just made, up here, we had a common denominator of 16, right? So what this cross multiplication does is it actually makes the common denominator the product of the two denominators. So the product of the two denominators is 8 times 16, which is a big number. What is it? 64 times 2 is 128. So the common denominator, if we just multiply the two denominators, is 128. But look at what this actually does. If we're taking 3 times 16, so if we look at 3 over 8 and we multiply it by 16 over 16, what we get is 48 over whatever 8 times 16 is. And then, on the other hand, if we look at 6 over 16 and we multiply it by 8 over 8, we're looking at 48 over, again, whatever 8 times 16 is. And this one works because of the commutative property of multiplication. So essentially, what we're doing here is we're comparing the numerators whenever our common denominator is just the multiplication of the denominator, is the product of the denominators that we already have. And that's why this cross multiplication works. It's just kind of the shortcut to looking at a common denominator that is the product of the given denominators. So this is kind of a nice thing to know, to explain, right? I feel like we should always be prepared to have students that want to know why things work, and we can give them a rule to follow, but you should really know why these rules are true, to kind of show that you know why everything's going on. So yeah, that's why the cross products work. It's just really, I guess you could say that comparing the cross products is just a special case of B, doing the common denominator. Okay, that's all for this page, and that's all for this video.